In the last lecture, we saw how to model probability for a randomized experiment. We defined something called a sample space, denoted by the symbol of omega. This was the set of all possible outcomes. Once sample space is given, we said that events are the subsets of this sample space. Another way to say it is that the set of events is the set of all possible subsets of the sample space. That means it is the set to the omega. This is set of all subsets of the sample space omega. The probability distribution function was defined to be a function from the sample space to real numbers such that the probability was always an element of 0, 1 for all the elements in the sample space. Secondly, if we sum up the probability over all the elements of the sample space, we get to be equal to. This is how we modeled the sample space. In this case, we assumed that the sample space was discrete. Once this is given to us, we can actually define the probability of an event. So the probability of an event S is an event, just sum over all possible elements in S, the probability of omega. This becomes the probability of the event. So in this case, we had a sample space and we defined probability over all elements of 2 to the omega in a consistent way. So this was our model. The problem is that in some cases it is not possible to define this probability for every subset of omega, for all subsets of omega. What should we do in this case? So let's see at least what should we define probability for. We will talk about events which are interesting. That means we want to talk about the probability of these events. There might be some non-interesting events for which we don't care about the probability. Set of interesting events. Can it be just arbitrary subset of 2 to the omega? Or it has to satisfy some properties? Intuitively, if A and B are our events, that means interesting events, A union B should also be interesting. Also, if A is an event, then A complement should also be. The probability of getting ahead is interesting, the probability of not getting ahead is also interesting, and so on. Using this intuition, we get something called a sigma algebra. Intuitively, this is the set of all interesting events. Formally or mathematically, this is a collection of subsets of omega such that they are consistent. What do I mean by consistent? One, the complete omega should be an element of this. So sigma algebra we will denote by script f. Complete set omega should be part of f. If A is part of f, implies A complement is part of f. And last but not the least, if A and B are element of the sigma algebra, then A union B is also element of sigma algebra. This can be extended to saying that if A1 to An are elements of sigma algebra, the subcountable union is also an element of sigma algebra. Using this laws, if you make a collection of subsets, this is called a sigma algebra. So this will be our set of interesting events. Again, we do not need to define probability of all the events. We only define probability over the elements inside this sigma algebra. You might have a question that why did we take union but not intersection? So this I will leave it as an exercise. Show that this F is closed under intersection. That means if A and B are elements of F, then A intersection B is also in F. Once such a sigma algebra is defined, you have a sample space, you have a sigma algebra, which is a subset of to the omega, then the PDF now is slightly different. The probability distribution function previously was defined from the sample space to R. Now we will define it to be from the sigma algebra to R. But it should be consistent. I can't assign arbitrary numbers to these probabilities. It should satisfy that the probability of the entire sample space should be 1. Secondly, if A and B are disjoint elements of the sigma algebra, then P of A intersection, P of A union B is PA plus C. These were the some laws which we derived after assuming our probability model before, but now we are saying that we can put any numbers to our probability such that they satisfy this condition. So this is the new model of we had sample space like before. We do not define the probability for all the elements in omega. Instead, we define a subset of to the omega. That means all the events and then give them probabilities such that they are consistent. This is the new way of defining probability. You can use this to prove that P of A intersection B is equal to PA plus PB minus PA union B as expected. So like in the previous case, this is what happens. And as an exercise, you can also show that the probability model in the previous version or previous lecture, you remember the discrete version, this is just a special case with the family being equal to 2 to the omega. What we discussed last time was a special case. This is a more generalized probability model. Let's take an example. We will take an example, solve it using the previous model and show that how can the new model be also. The question is simple, answer is not very difficult. We will focus on the model. How do we model the probability? In a family of 5 kids, what is the probability that there are more girls than boys? I'm sure you can solve this question. Let's do it formally. The first step to define the sample space omega. In this case, it is all strings of length 5 of G and B, where G denotes girls and B denotes boys. This is our sample space, and then the size of this omega is 32, it's to the power 5. Now we take the sigma algebra to be set of all possible events. Now we are modeling the discrete version, so we will use the model discussed in the previous class. So everything is an interesting set, and the probability distribution function will be from omega to R. So we see that we can just say that all strings are equally likely. So all strings have probability 1 over 32. You can easily check that 16 of them have more girls than boys. This implies that the answer is Number of girls are more than number of boys with probability half if the family had 5 kids. Nothing special about this. We did it using the previous model. But we can also do it using the new model. How will we do it? Define A to be the event that we have more girls. The sample space remains the same. A complement to be the event that we have more boys than girls in the family. If this is the case, look at this set. It has the empty set, it has the whole set, A and A complement. You can easily prove that F is a sigma L set. This is something which you should do on your own. We only need to define probability over just these sets. Now we know that P of omega is equal to 1. And since girls and boys are symmetric, we can also assume that P of A is equal to P of A. Now applying the laws of probability, P of A plus P of A complement should be equal to P of omega equal to 1. This is by the laws of probability and implies that the probability of A is half. So we get the same result, but in this case we did not define probability of all strings. We only define probability for things in this sigma L set. Do the same thing when we have 6 kids in the family. You might still say that we really did not need the new model. The same thing could have been done with the discrete version as we did here. So in the next lecture, we will see continuous sample spaces and see that this generalized model is really necessary.